is the thermal conductivity. Okay, thermal conductivity. What is the meaning of the thermal conductivity? So the word conductivity, that means the conduction, and thermal conductivity means the conduction of thermal energy, meaning that the movement of the thermal energy from one point to the other. And previously we already discussed three different actually ways of, you can say, transfer of heat energy from one point to the other. And they were, for example, conduction, convection, and radiation. Because this one is the thermal conductivity, so it is mainly related with the conduction process. In the conduction process, we learn that, for example, that we do have one material, and this is, for example, some kind of a rod, and this rod, we actually put it, for example, on fire, and just consider that this is the fire. And then what we are getting? We are getting the thermal energy. So we are heating up this rod. And when we will be heating up this rod, what will happen? The thermal energy that will conduct inside it, and it will move to the other part. Those are the actually at low temperature, isn't it?
Yes.
So if, for example, we consider that we do have different rods, and all have different kind of properties with respect to the material, for example. And then what we did, we put some kind of wax, for example, at the end of this rod, and we say that this is our rod number A. And then we put an other rod, and in the same configuration on the same fire, and the all three rods, they also have you can say the same size and same length, means. So, and then again at the end we put some wax also, and we call that this is our rod number B. And then we consider the third rod, and the third rod is again of the same actually the size, and we place it on the same fire, and the wax at the end of this rod. Okay, so now the condition here is that in all of these three rods, what could happen, that they will get thermal energy from this source of fire, and that thermal energy will conduct inside these rods from hotter part toward the cooler parts. When this thermal energy will reach at the other end where we put wax, then that thermal energy will start to melt the wax. Okay, isn't it?
Yes.
Yes. And if, for example, I say that what happened, that the wax on number 3, that actually melted first of all. So this wax actually melted down before the other two rods. What does it mean? It means that the thermal energy was conducting faster in rod number C compared to B and A, isn't it?
Yes.
Yes. So what does it mean? It means that the rate of flow of thermal energy, the rate of flow of thermal energy, thermal energy, let's say we call it ET, thermal energy is higher compared to the others in C, isn't it? Okay.
Yes.
So what does it mean? It means that the thermal conductivity of rod number C is much higher than the other two rods. Okay. So then This also actually tells us, because in the beginning, what we said, that these all rods are identical in shape and size, isn't it? So then what could be the difference? Difference here is that they are made of different materials. If they are made of different materials, then we can say that the flow of heat energy, it depends on the type of the material or the material properties. So then in this way, we can actually establish our concept that thermal conductivity depends on material properties. Material properties, isn't it?
Yes.
Yes. So if, for an example, we have metals, we do have, for example, metals. So in metals, usually the rate of flow of thermal energy is much higher compared to insulators. In metals, it is quite much higher. But in insulators, in principle, it is actually lower. Insulators, so in insulators, quite much, it is quite much lower. Why? Because there this thermal energy, in fact, actually conducts pretty much slower. And in metals, we also have free electrons. Those also help to conduct thermal energy. But still, there are some insulators in which the thermal energy can conduct better compared to electrical energy, or because in case of the electrical energy, you always need free electrons for conduction. But for the thermal energy can not only conduct with the help of electrons, but also with the ions or the atoms of the material. Insulators still have the atoms. So then the properties of the material will define the thermal conductivity. Okay, understand? And now you can also understand one more thing, and this is the isolation. What is it? It is the isolation, that how we can isolate, for example, our homes, particularly in the winter, that we can keep our homes, you can say, warmer for a longer time. For an example, that we do have a house, and this house we want to keep it warm for a longer time. So in that case, what you need? You need to heat it up first. First you need to heat it up. Once you have heated it up, then your next, you could say, the objective is to keep it hotter for longer time. So in that case, what would you try? You would try to avoid this flow of heat energy from inside to outside. And how we can avoid it? By isolating, for example, the ceiling of this house, and you could say also the walls in a proper way. And of course, and the windows as well, or the doors. How we can do this? If, for an example, we put some insulating material, if we put some insulating material here to isolate the outer side of the ceiling and also the wall like things, and for the ceilings, mostly people actually use this fiberglass and some kind of, you can say, isolating foams like, and those are keeping the thermal energy inside and keep our homes warmer for longer time. Okay, understand?
Yes.
Very good. Any questions so far?
No, sir.
Okay, so now we can actually then move ahead to the other topic related to the heat and the temperature. Okay, so here we discussed the flow of the thermal energy. Okay, and another thing that, for example, you want to check that that thermal energy here is higher or here is higher. So very easy way of checking is that what temperature is here and what temperature is here, isn't it?
Yes.
Okay, so with this concept, let's move ahead. And now we want to discuss about specific heat capacity. Specific heat capacity. Okay, what is it? So, for example, we have, uh, let's say that we have a piece of metal, a piece of metal, and we have for example, a piece of rock, and this is some kind of a rock. Okay, and both are sitting in the sun, and sun is actually the summer sun, and it's very hot, for example, and both of these pieces are getting the same, you can say, the thermal energy. And after a while you check that, you check the temperature of metal and temperature of the rock. What you think, which material will actually have higher temperature?
The metal.
Metal. Why the metal will have the higher temperature? Because it's easy to warm it up compared to rock. Okay, that means that heating up, or you can say giving the temperature or increasing temperature is easier for a metal compared to rock. Okay, then, before going into details, that let's understand what is the meaning of a temperature. So temperature is, you can say that, for example, we have some material and it has its main particles, and these particles are like atoms or the molecules, and their vibrations, and this actually vibration is because of the energy these particles have. The average energy of these all particles will define its temperature. Okay, average energy of these particles will define its energy. So now some materials, it is very hard to give the vibration or give the energy to the particles if they are very strongly, you can say, positioned or fixed at their positions. And some materials, it will be very easy for us to warm them up. Okay, and that what is the case of the metal compared to rock. Then here we understand our one point, that increasing the temperature
To the forest.
depends on type of you can say the, we can again say material property. Material property means that what kind of material you are using. Okay,
Yeah.
properties. Okay, and now then we actually go to the next point. So our next point is that, for example, now you have already understood that what is the meaning of the temperature. So keep that concept in your mind, and we consider that we do have two pieces of metal, and one is a small piece and one is a bigger piece. So it means that it has a larger surface area. It has a larger surface area. And now we want to heat them up. Heat them up means that we want to increase their temperature. Okay, for an example, both are at 20 degrees centigrade, and this is also at 20 degrees centigrade. I want to increase its temperature to 30 degrees centigrade. And this one also, I want to increase its temperature to 30 degrees centigrade. Okay, which piece, you can say, you can easily heat it up? The smaller piece or the bigger piece?
Smaller piece.
Smaller piece. Okay. Then you can also understand this in another example, that for example, you want to boil that water, and this water is, you can say that, for example, that you have a very small amount of the water here. And if you have a small amount of water, and in another example, that if you do have a very large amount of the water, so of course, it will be very easy for us to boil the smaller or the lower quantity of the water, isn't it? So this actually, if you will have the more quantity, then it would mean that you need more time or more energy is required. More energy is required to heat it up. And it is the same here, that for this smaller piece of the metal, you need less energy to heat it up. But in this case, you need more energy to heat it up. Then that means that to the increase in the temperature also depends on mass of the object, isn't it? Or the material. That if mass is more, then you need more actually energy. For example, that if you are going to distribute some money among some people, there are only two people and you have 10 pounds, each will have 5 pounds, so they will have some energy to buy a good sandwich. But if, for example, you have 10 pounds and there are 10 people, so each will get 1 pound, and that would not be really very good to get a good sandwich, isn't it?
Yes.
So then they will be still hungry. So their temperature will not be high enough compared to two people, isn't it?
Yes.
Yes. So then this is actually the thing, those that we understood. Now we combine our previous example that we took for understanding thermal conductivity. In that case, we understood that the thermal conductivity depends on the type of the material, that what kind of a material we are using. And then in another way, you can say that the thingy, for example, here that we discussed with the type of the material. And now the last concept is that, for an example, that we do have two metal pieces. Those are of the same surface area and same properties. And then this material actually exposed to, you can say, the greater energy, meaning here actually the energy is higher and here energy is lower. So for example, you can consider that we do have water in both of these pots, and the level of the water is the same for both of these actually pots. But this one, you have a higher rate of, you can say, the burning of the gas compared to the other piece. So which one will heat up first, or the boil up first? That will have higher energy, isn't it? That will have higher energy. So you can boil it up easily. Then it means that it also depends that how much energy you are providing, isn't it? That
Yeah.
how much energy you are providing. Then what does it mean? It means that the energy which you are giving, that is proportional to the temperature, isn't it?
Yeah. Yes.
Okay. So just let's start with this concept and try to establish our, you can say the, here, let's also write one third point, that amount of energy, isn't it?
Yeah.
Yes, very good. Okay, now let's try to establish a mathematical formula, and that what we can do together. So we said that the energy is proportional to temperature. This theta is temperature. So this is temperature.
Look at just.
And here, this is our, you can say the thermal energy or the heat, or we can simply say this is our energy. Okay. So this is energy. Now, if I increase energy, meaning the change in energy will be equal to the change in temperature. So with this actually understanding, you can actually develop a concept that if we are going to increase this energy, then of course temperature will also increase. But if we will decrease this energy, we will take out the energy, then this temperature will also decrease, isn't it?
Yes.
Yes. Okay. So then this concept has been included, has been included. Now, what we do have, we have the next, let's say this is our mass. This is our mass, the concept of mass, that how we can include the mass here. So if, for example, we have a larger mass, for the larger mass, we need larger amount of energy to give some particular temperature, isn't it? That, for example, if mass is bigger, then of course you need to give more energy to bring it at some certain temperature. As I gave you an example of distributing 10 pounds among two people and 10 people. So you can say if I distribute 10 pounds in two people, among two people, between two people, and 50 pounds among 10 people. So then you can say that in both cases, everyone will have 5 pounds, isn't it? Everyone will have 5 pounds. So here you understand that if the mass is larger, you need larger amount. Then that means again energy and mass, they will also be directly proportional. Understand?
Yes.
Okay. And now what we can do, we can actually here have you can say this formula. So this formula is actually taking care of mass and energy in the relation of the temperature. So what about the type of material, that how we can include that in this formula? So that formula means that, for example, we convert this equation into equality, and there is a constant of this proportionality, which is C, and mass of the material and change in the temperature. So here what we did, we put C, and this C, it depends on the properties of the material. It depends on properties of a material. So it means this C is constant for one type of the material. If you will change the material from metal to rock, then this C will also change. And this C, that actually called specific heat capacity. This is the specific heat capacity. Okay, understand?
Yes.
Okay, very good, very good. So far, so good. So now we can try to establish the definition of heat capacity. So for that, let's go to the next page and we rewrite the formula that we just established as this just established. So this is the change in energy. We said that will be equal to heat capacity times the mass times the increase in the temperature. So this delta means change in temperature and this delta means change in the energy. Okay. And from this equation, we can see that the C heat capacity is equal to the energy per mass per change in the temperature, isn't it?
Yes.
Yes, okay. So if I say that I want to calculate the heat capacity for 1 kilogram mass of a material to increase 1 degree centigrade only. So 1 degree centigrade temperature that I want to increase of a 1 kilogram material, then you can say that this C is in fact the change in energy or the energy required to heat up 1 kilogram to 1 degree centigrade, isn't it?
Yes.
Yes, so from this formula, you can understand the concept of heat capacity. So the heat capacity is that you can say the amount of heat energy required to increase the temperature to 1 degree centigrade of 1 kilogram mass of an object, isn't it?
Yes.
Yes. So this is our actually the main definition of heat capacity. Okay, understand?
Yes.
Any questions so far?
No, sir.
Okay. So here we already said that this heat capacity is the material property. It is the materials property. If this is materials property, that means that every material will have different value for heat capacity, isn't it?
Yes.
Yes. So, for example, we give an example of water. We give the example of water. The water's heat capacity is 4200 joule per kilogram per degree centigrade. So, what does it mean? It means we always need 4200 joule heat energy to increase temperature by 1 degree for 1 kilogram water, or you can say approximately 1 liter water. Okay. Then, for an example, we do have iron. We do have iron. So, in case of iron, we have the heat capacity of 390 joule per kilogram degree centigrade. So here you can actually also compare very easily between these two materials, that iron is a metal and here it is very easy to heat it up. Okay, understand? Do you understand?
Yes.
So if you want to increase the temperature of iron by 1 degree centigrade, you need only 390. But for the same increase of the temperature in case of the water, if both have the same amount like 1 kilogram, then for the water, you need 4200 joule energy, isn't it?
Yes.
So this is actually the meaning of heat capacity. So this actually tells us that how we can actually increase the temperature and which factors are important. Which factors are important to increase the thermal energy, to increase the temperature of a material. Understand?
Yes.
Okay, very good. So now we can go to an exercise and we can solve some questions together. So for that, it is your actually now task. The very first question that I have, that okay, I will quickly write it. A small bucket of water and a bucket of water, sorry, and and a large bucket of water are left in strong sunlight, in strong sunlight, which one warms up faster? Give a reason. So this question will have 2 marks.
It will be the small bucket.
Small bucket. So why?
Because it has a small mass.
It has a smaller mass.
Yeah.
So in the exam, when you want to give actually the answer, because you see, it is a 2 marks question. So then you need to give at least 2 points, meaning 2 points means that you say that the smaller bucket have smaller mass. What would you say? The first line, the smaller bucket have smaller mass, and according to the equation of heat capacity, the energy required to increase temperature directly proportional to the mass. Okay, understand? Then,
Yeah.
or you can actually say this in a better words, because this you can say we looked at, because increase in temperature, you can see that this delta theta that depends on the delta E divided by C and M, isn't it? If mass is smaller, the temperature change will be bigger. If energy and heat capacity are constant, isn't it? Because in both cases, it was water. So C is constant. And energy, and they are both in one same, actually the stage, same situation, the strong sunlight, and then only the mass, those are inversely proportional to each other. So if you will give the answer in this way in the exam, you will get your all 2 marks. Okay, if you will only write the smaller bucket, so then maybe you will get only 1 mark. Okay, understand?
Yes.
Very good. So now we go to the next question. The next question is uh, number A, the first part, that explain information, no. Explain why a mass of lead heats up more quickly than an equal mass of aluminium. So here, before actually you give the answer, I would see that, tell you that the heat capacity of aluminium is equal to 900 joule per kilogram per kilogram per degree centigrade. Okay, per kilogram. Okay, it should be small, sorry. And in case of lead, in case of lead, it is the C, the C of lead is equal to what? Let me check. 130. 130 joule per kilogram degree centigrade. Okay, now do you understand this question? Explain
Yes.
why a mass of lead heats up more quickly than an equal mass of aluminium.
It's because lead has a lower specific heat capacity than aluminium, so it uses less energy to heat up.
Yeah, exactly. Yes. This time, actually, you give 2 reasons. One, first you gave one reason and then you answered it. So you said that aluminium have higher specific heat capacity compared to lead. The second point you said that it means we need less energy to increase the temperature of lead compared to aluminium. So that's why aluminium, lead will have higher temperature. It will be easy to heat up lead. So you will get both marks. Okay, very good, Shabash. So now we go to the question number B part of this one. The B part is that calculate the energy needed to the temperature, raise the temperature of 0.2 kilogram of aluminium from 15 degrees centigrade to 40 degrees centigrade. Okay. Now you see, you already remember, you already actually know the heat capacity of aluminium. So then you can very easily calculate it. How would you calculate? You see, here we already know the heat capacity of aluminium, which is 900. Yes, Muzamil beta. So let's, you see how I would actually, this is energy. There is also E. Okay. So how I would calculate here, first of all, I will take out data. So this data is that calculate energy needed to raise the temperature of 0.2 kilogram of aluminium. So then it means mass is equal to 0.2 kilogram, for example, and this is aluminium. So heat capacity of aluminium is 900 joule per kilogram degree centigrade. And next is that temperature need to increase from 15 to 40, isn't it?
Yes.
Yes, very good. So then what we can do, we can calculate delta theta. So this delta theta is the theta final, meaning temperature final, minus theta initial. So this is 40 minus 15. So delta theta is in fact 25 degrees. Okay. So in some questions, they can give the temperature information like that, a 15 degrees centigrade to 40 degrees centigrade. And in some cases, they can actually only say that we want to change of this much. So they can directly give you theta. So in both cases, you can calculate the theta. And you see what we need to calculate? Energy needed. So required energy is delta E. Required energy is delta E that we need to calculate. And we know this formula that delta E is equal to what? C, heat capacity, mass times delta theta. Okay, understand?
Yes.
Very good. So here you can put 900 times 0.2 times 25. So this is a half. So answer is 450, isn't it? 450 joule, isn't it?
4,500.
You are right. Because it will be double, isn't it?
Yes.
It will be 5 times. So this is 0.2 times 25. Answer is 5. So 5 times 900. Yeah, you are right. This is the answer. Very good. So if you can see, you can remember this formula with the concept. The concept is that, for example, you say we have 1 kilogram water, and what we want to do, we want to increase its temperature by 10 degrees centigrade. When I say I want to increase its temperature by 1 degree centigrade, okay, it means that delta theta is equal to 10 degrees centigrade, isn't it?
Yes.
Yes. So we know that for 1 kilogram, to increase each degree centigrade, we need how much energy? 4,200 joule energy, isn't it?
Yeah.
And then for 10 kilogram, we would need, for 10 degree centigrade, we would actually need 10 times, isn't it?
Yes.
Yes. And if our mass is 2 kilogram, then it means it will be double, isn't it? And more energy you would require, isn't it?
Yes.
Yes. So now I guess this actually the concept is pretty much clear to you, isn't it?
Yes.
Very good, Shabash. So now we can go to the next point. The next point is I asked you about aluminium, isn't it?
Yes.
Okay. Then now calculate uh, calculate the energy required to raise the temperature of 0.4 kilogram of water uh, by 30 degrees centigrade. Mhm.
Is it
Okay.
50,400?
How much?
50,400.
Okay. So let me see. Sorry. So we have a heat capacity of 4200 and how much mass? 0.4 and temperature increased by 30. So delta theta is equal to 30 this time, isn't it?
Yes.
So this is the required amount of energy. Very good. Yes. So 1.2 and why don't you be 1.4 times? How much you said?
50,400.
50,400.
Yes.
Are you sure?
Hmm?
Are you sure?
Yeah.
Okay, so times what am I doing? So 30 times 4 answer is 12. Is sorry, zero point 0.4 answer is 12, isn't it?
Wait, what?
So 0.4 times 30 answer is 12. 12 times 4200 is equal to yes 50,400. Yeah, you see we need actually a 50,400 joule energy. So if we actually have not water, we have lead. We have lead. And in case of lead, we know that the heat capacity is 130, isn't it? But if it will be lead, then how much energy we need to heat it up to by 30 degree? So this will be 130 times 30 times 0.4 kilogram, if the same amount. So then what is the answer? Can you do quick calculation, please?
1,560.
1560. 1560 joule. You see here, so big difference, just 1506. So you can say 1 against, sorry, 50 against 1.5, isn't it?
Yes.
Yeah, so this is a so big difference. So lead, you can heat it up very, very easily compared to water, compared to water. Okay, so then. Hmm. Okay, so now let me change my question. This time we have a different question. We again need to calculate energy to raise the of temperature of 0.4 kilogram water in aluminium container. Okay, aluminium container of mass 0.4 2 kilogram of mass, 0.2 kilogram, from 15 degrees centigrade to 40 degrees centigrade, because we want to take a bath. That's why we need 40 degrees centigrade. Okay, Muzammil beta, can you do this? What would you do? Mm-hmm. Mm-hmm. Muzammil, what would you do, beta?
I don't know for that one.
You are thinking?
Yeah.
Okay, good
Would you
thing.
find the average thing?
Mm-hmm.
I don't know.
You don't know.
No.
So let's make a picture. Uh, picture of this question. The picture of this question, just give me a second. So you see what you do have, you have a container, and this container is made of aluminium, okay? And then inside we put water, 0.4 kilogram. And where is the fire? The fire is here. Fire is here. Okay. If fire is here, that the fire is heating up the temperature of water. So it means that first you need to increase the temperature of aluminium, and then the aluminium will transfer the energy to the water, isn't it?
Yes.
So if you want to increase to 40 degrees centigrade, then it means you also increasing temperature of aluminium to 40 degrees centigrade, isn't it?
Yes.
Yes. So that means you are actually the total energy that will be consumed, the total energy that will be consumed will equal to the energy required. That will be equal to energy required to heat up aluminium plus energy required to heat up water, isn't it?
Yes.
So in this case, we would actually calculate separately. We will calculate separately. So this only mass is different. Is for example, aluminium is 0.2. Heat capacity is 900. We remember because we already used. That's why I am not going to give you here. But in exam they can give you this value. Okay, 900. And how much temperature we want to increase? From 15 to 40. So this is actually 25, isn't it?
Yes.
25. And plus 0.4. So this was actually 0.4. Here is the point, okay? 0.4, then times 4200, which is a heat capacity, and temperature increase, of course, the same, isn't it?
Yes.
Now you have two different, actually, the heat capacities of two different materials, because we want to bring them both at the same temperature. So that's why you need to consume energy for two different materials, isn't it?
Yes.
Yes, that what you will calculate and will put it at one single position. So what will be that answer?
We got 46,500.
Okay, very good. So let's go to the next page. So here we got the last question. So last question is that a copper water tank, meaning that we can put water in that of mass 20 kilogram, of mass 20 kilogram, contains 150 kilogram water at 15 degrees centigrade. Okay, now calculate the energy, calculate the energy needed to heat the water to heat the water and tank to 55 degrees centigrade? So this is the same question, isn't it? Can you find the answer? What would you do? I'm sure this time you know how to do that, isn't it?
What's the specific heat capacity of copper?
Ah, so heat capacity of copper. Very good. 385. So is of copper is equal to 380, 385, yes. And for water, you know, 4200.
Got 25 million and 508,000.
Sorry, just 1 second. So what you said?
I got 25 million and 508,000.
25 million. Okay, because here, why it is 20 million? Because you see, this is a very big number. So 20 kilogram is copper and 150 kilogram is water. So simply, so you can say 4200 and times 150 and times that we want to go from 15 to 55, then it means the here it's a 40. So every number is pretty high. And this is 66,000, isn't it? And isn't it?
Wait,
20,
what?
24.2 million, isn't it?
No, I got thing. 25 million.
25 million, you said.
Yeah, for the total.
25 million. Ah, sorry. Yes, yes. This is 24.2 million only for the water, and then the rest will be for the copper, because copper has a very low heat capacity compared to uh, the water, isn't it?
Yes.
Yes, very good. Now this is the last question. Sorry, because we solved all questions of the same type. So here I make actually a little bit different. At this time you need to increase in the temperature. That how much temperature will increase of 2.5 kilogram water if we are providing 50,000 joule energy.